Hello everyone and welcome back to Math Made Easy. In the previous lecture, we started the interpolation section of numerical analysis and started the Lagrange interpolation method. We learned how to estimate the value of a function when only a set of discrete data points is available. We also saw an important advantage of Lagrange interpolation. The given x values don't have to be equally spaced. But in today's lecture, we're going to study a different interpolation technique where the spacing of the data points become extremely important. Our topic is Newton's forward interpolation method. The word forward here is very important. This method is particularly useful when the values of x are equally spaced and the values we want to estimate is near the beginning of the given data table. So instead of constructing the interpolation polynomial directly using the Lagrange basis polynomial, Newton's method uses a finite difference table. And this makes the calculation systematic, especially when we have several data points. So today we'll understand what these finite differences are and how to construct a forward difference table and how this Newton's forward interpolation formula is derived, meaning of U, the complete algorithm, and followed by a detailed solved example. So let's just begin. So suppose we have the following data as x value as 10, 11, 12, 13, 14. This fx value is 100, 121, 144, 169, and 196. And suppose we want to estimate this f at 10.5. The x values are equally spaced here, as this 11 minus 10 is 1, 12 minus 11 is 1, and so on. Also, this 10.5 is closely related to the beginning of the table. So this is exactly the type of situation where this Newton forward interpolation is useful. So before applying Newton forward, always check the spacing first. And we define this common interval as this h equals to xi plus 1 minus xi. For equally spaced data, this h must remain constant. For example, if I take this 2, 4, 6, 8 and 10, having this common interval as h is 2. Therefore, the data are equally spaced. But consider something like 2, 3, 5, 8 and 12. Here this 3 minus 2 is 1, this 5 minus 3 is 2, this 8 minus 5 is 3. So spacing is not constant here. Therefore, we can't directly use the standard Newton forward formula here. And it's a very common examination mistake. Now let's just understand the central computational idea of Newton's forward interpolation. The forward differences. Suppose we have this y0, y1, this y2, this y3 and up to so on. And the first forward difference will be this del yi equals to yi plus 1 minus yi. And for example, if we take this y0 as 10 and y1 as 15, then this del y0 becomes 15 minus 10 equals to 5. Now comes the second forward difference, which is obtained by taking the difference of the first differences. So this del square yi becomes this del yi plus 1 minus del yi. Similarly, this del cube yi becomes del square yi plus 1 minus del square yi and up to so on. So suppose our data are somewhat like this x as 0, 1, 2, 3 and 4 and this y as 1, 4, 9, 16 and 25. Now constructing the forward difference table, for that we first need to evaluate the first differences. That is, this del y0 becomes this 4 minus 1 is 3. Del y1 as 9 minus 4 is 5. This del y2 becomes 7. This del y3 becomes 9. And the second difference is as del square y0 becomes this 5 minus 3 as 2. Del square y1 becomes 7 minus 5 as 2. And this del square y2 becomes 9 minus 7 as 2. And the third difference is hence y del 3y equals to 0. So our table becomes this x, y, del square y, del cube y, where x values are 0, 1, 2, 3, 4, and this y as 1, 4, 9, 16, 25. And this has 3, 5, 7, 9, and this is 2, 2, 2, and hence 0. Now notice this triangular structure, and this is called the forward difference table. Now let's just derive the actual interpolation formula. Let the equally spaced data points be this x0, x1, and x2, with this xi as x0 plus I times h. Suppose we want to find the value of x, so defining this u as this x minus x0 whole divided by h. And this parameter tells us how far x is from the first tabulated value measured in units of h. And this Newton's forward interpolation formula becomes this yx equals to y0 plus u times del y0 plus u into u minus 1 divided by 2 factorial del square y0 plus u into u minus 1 u minus 2 and whole divided by 3 factorial into del cube y0 plus up to so on, where this u is x minus x0 by h. Now let's just break this formula down. The first term is simply this y0. Then we add the first difference correction as u into del y0. And the second difference correction will be u into u minus 1 divided by 2 factorial into del square y0. And the third difference correction is u into u minus 1 u minus 2 divided by 3 factorial into del cube y0. And this continues depending on the number of available data points. Now notice that all the references are taken from the first row only. This del y0, this del square y0, and this del cube y0. And this is an important characteristics of Newton forward interpolation. Now when should we use this Newton forward? There are typically two conditions you should always remember. The first condition says this x value should be equally spaced. That means this h value must remain constant. And with the second condition, we have this required value of x should generally be near the beginning of the table. For example, if the table begins at x0 as 10 and ends at xn equals to 20, Newton forward is more convenient when the required value is near this 10. And if the required value is near the end of the table, we generally prefer that method as Newton backward interpolation, which we will study later. So to summarize this all, we just need to arrange the given values of x and y first, and then checking that x values are equally spaced, calculating that h value, and then constructing the forward difference table. Identify your first values as is y0, del y0, or del square y0, and up to so on. And hence calculating the value for u and substitute into the Newton forward formula. And hence calculating the required interpolated value. So now we have an example where we need to estimate the value of f at 1.5 from the following table, where we have this x and fx values. This x is 1, 2, 3, and 4, and fx is 2, 5, 10, and 17. Now checking the spacing between them, as h is equals to 2 minus 1 as 1, 3 minus 2 as 1, this 4 minus 3 as 1. Therefore, this h becomes 1, and the data hands are equally spaced. Now constructing the difference table, for that we have this first differences as this del y0 as 5 minus 2 as 3, del y1 as 10 minus 5 is 5, this del y2 as 17 minus 10 as 7. And the second difference is as del 2 y0 as 5 minus 3 is 2, and this del square y1 as 2 again. and hence the third difference becomes 0. Now we have the table where we have this x, y, del 2y, del 3y, where this x has 1, 2, 3, and 4, and y has 2, 5, 10, 17. And this del y has 3, 5, 7, and this has 2, 2, and hence 0. Now calculating the u values, since we need x as 1.5 and this x naught as 1 and h is equals to 1, so we have this u value as 1.5 minus 1 by 1 as 0.5. Now applying the Newton forward formula, where we have this y as y naught plus u times del y naught plus u into u minus 1 divided by 2 factorial del 2 y naught. And hence this is 2 plus 0.5 times 3 plus 0.5 into minus 0.5 divided by 2 into 2, and hence this becomes 2 plus 1.5 minus 0.25, and hence this f at 1.5 becomes 3.25. Now notice that this agrees with the Lagrange interpolation result for the corresponding quadratic data. So today we studied the Newton's forward interpolation method. We learned that this method is particularly useful when the data points are equally spaced and the required values lies near the beginning of the table. We introduced the forward differences, constructed the forward difference table, derived the Newton forward interpolation formula, and calculated parameter u, and solved the numerical example step by step. And the key formula to remember is this Newton forward formula. And remembering the two most important conditions as the equal spacing and the point near the beginning of the table. In next lecture, we'll study the Newton backward interpolation method. The idea will be very similar, but instead of starting from the beginning of the difference table, we will work from the end of the table and making it particularly useful when the required value lies near the last tabulated point. So thank you for watching, and if you found this lecture helpful, don't forget to like and share and subscribe to Math Made Easy, and I'll see you in the next lecture.